my name is Martin Tappler, and in the following I'm going to present adaptive shielding under uncertainty. This is joint work with my colleagues at Graz University of Technology, Stefan Pranger, Bettina Könighofer, Martin Deichselberger and Roderick Blum, and with Niels Jansen from Radboud University Nijmegen. In shielding, we take existing controllers and alter their behavior in a way to enforce safety or to improve performance. Adaptive shielding here means that we adapt to new situations, to changing situations. And uncertainty arises from the stochastic environment. We consider shielding for performance, and we are given learned controllers that have been trained for some form of optimal performance, for instance learned using reinforcement learning, and we shield them. Concretely, we illustrate shielding in a traffic control scenario where the goal is to minimize the waiting time of cars. So when we now want to change a learned controller, we face several challenges. It may be hard to add secondary objectives or new features, such as adding a bus lane to the crossing shown on the slide here. The controller may show poor performance in untrained situations, so situations that have not been considered during training. For instance, an accident during operation may cause traffic patterns that have never been seen before and which the controller cannot handle. And local fairness may be hard to guarantee, so a farm road with low traffic may never or rarely see a green light. To tackle these challenges, we propose to apply shielding. And for shielding, we assume a setting as is shown here. So we have an environment, and we have a learned controller and a shield. The learned controller observes the environment and sees and knows of some costs associated to its actions, and proposes some action to be performed on the environment. We intercept the controller actions with a shield and may override it by a shield action if it is necessary. We model this setting using a Markov decision process. So we model the environment and the controller as being stochastic and consider the task of shielding as a Markov decision process. So concretely, to compute the shield action, we solve the Markov decision process with a mean payoff objective to achieve the shield objective with minimal interference. So we only want to interfere with the controller if it is actually necessary. We don't want to change the action proposed by the controller if it is not necessary, as we assume that the controller generally works well. So here you see shielding in action. We simulated the traffic in Helsinki using the Sumo traffic simulator, and we did this in two setups. In one setup, we shielded the traffic controllers of 6 crossings, and in another setup, we did not deploy shields. Whenever you see some red flashing there on the left-hand side, the shield interferes with the traffic controller and changes the traffic light setting. So here in the following you see that we will simulate a traffic accident that blocks a part of the road. This is shown here in yellow. So the shield now needs to adapt to this new situation and change accordingly. Now if we look closely, we see that on the right hand side traffic jams occur, whereas on the left hand side the traffic flow is still good. Now I want to discuss how we compute shields. So we take the Markov decision process model and assign costs to state action pairs. The shield then is basically a policy, so a policy for choosing actions in the Markov decision process that minimizes the costs. We achieve optimal shield performance with minimal interference via a weighted sum of costs actually. So we have two cost terms. One is proportional to the shield objective. So For instance, this can be the waiting time of cars here or the waiting yellow dots, and if we want to add a bus lane. And one is a constant cost that we assign to interference. So as we want to have minimal interference, we assign some cost to that. Then when we have augmented the Markov decision process with the cost, we solve a mean payoff game to minimize the long-run weighted average cost. An optimal shield is then an optimal policy that minimizes this long-run weighted average cost. So in the previous slides, I assumed that we have a model of the environment. So we require for shielding a faithful environment abstraction. But in many cases, we don't know an exact model. And we may also need to adapt to new situations that we have not modeled before. So we need to adapt to accidents that change traffic patterns. We solve this problem in adaptive shielding via three main techniques. So we continuously observe the environment and learn environment models. We abstract these models to create abstract models, and then we solve mean payoff games for shield generation. And whenever we see that an abstraction is too coarse, we refine it. So we perform these three techniques continuously at runtime. Let's see how this works for the traffic control situation. So we observe a crossing as the one shown here on this slide, and we observe how many cars are waiting and what the traffic controller setting is. In this way, we observe traces of the form shown here below, where we have states that correspond to the number of waiting cars in the traffic controller setting, and we have edges that are labeled with the shield actions. And here we see in the first step, we have 6 waiting cars in the north direction, and the shield does not interfere. It leaves the traffic controller setting to east-west. Only after in the third step, the shield interferes and changes the traffic controller setting. Now we take such traces and learn a Markov decision process model from them. So here you see a part of a Markov decision process that we learn, and we perform abstraction of the model. We take these models now and compute a shield by solving a mean payoff game on them. Finally, we deploy the shield and continue with the traffic light control and observe the environment. So we perform all these steps continuously at runtime, and at regular intervals we update our knowledge by learning new models and computing new shields. Model learning in this scenario works as follows. We have a non-stationary Markov decision process with unknown dynamics. Unknown dynamics because we don't know beforehand what the traffic patterns are. And we have a non-stationary MDP because the traffic changes over time, as I said. So we have we need adaptiveness. Now the task here is to estimate multinomial distributions for the transition probabilities in the MDP. So we estimate the probabilities of reaching some state J by an action A from a state S. We do this via an online estimation of probabilities. Concretely, we initially start with a symmetric Dirichlet prior distribution with some hyperparameters alpha, and we update them using a learning rate. And whenever we need to learn a model, we estimate the transition probabilities using the hyperparameters. In abstraction, we lump together states, so we combine states that have a low probability of being reached. In the traffic scenario, we abstract away states that correspond to traffic situations that are never observed. So now let's discuss the evaluation. As I said before, we evaluated shielding in a traffic simulation of Helsinki, and we simulated that the city highway is blocked. Here you see some plots of the accumulated waiting time of cars in unshielded operation and in shielded operation. And we shielded 6 crossings that are on a detour that cars need to take when the city highway is blocked. In red you see that the accumulated waiting time of cars increases over time in the unshielded case, whereas when we perform shielding, the accumulated waiting time decreases. What we also see is that shielding performance is robust with respect to the concrete setting of the interference cost C2. We also added a feature to a traffic controller where we added bus prioritization over cars. And here in the upper part of the slide you see the accumulated waiting time of cars, and on the lower slide you see the accumulated waiting time of buses. And you can see in shielded operation the accumulated waiting time of buses can be decreased successfully in comparison to the unshielded case. On the upper part you see that the accumulated waiting time of cars increases, but it also does not explode. So we do not cause traffic jams using shielding here. So to conclude, I presented adaptive shielding to improve existing controllers, which we do by learning Markov decision processes from observations, and we solved them with mean payoff objectives. We evaluated our approach on crossings in Helsinki and saw an improvement of waiting times. For future work, we would like to investigate additional ways to learn from observations and to consider also hybrid scenarios where we also have non-discrete aspects.